Well, welcome to Doc Onco's Physics. My name is Keith Onco, and today what we're going to be doing is taking another look at a kinematics problem in one dimension. This time what we're going to be doing is we're going to be looking in the y dimension. Thus far in some other problems we've looked at strictly in the x dimension, and today we want to look in the y dimension. The problems are essentially the same. We're still going to use the same set of equations, right? It doesn't change at all, except now they are y dimension variables. We're still going to use our table, except they're y dimension variables in the table as well. So nothing really changes, except that anytime we have something going on in the y dimension, we're always going to have one thing that we do not always have in the x dimension, and that one thing is acceleration due to gravity. If we're here on the surface of the Earth, we're going to have an acceleration due to gravity that's always going to be negative 9.8 meters per second squared. In the problem that we're about to do, we're talking about acceleration due to gravity that's not going to be 9.8 meters per second squared because we're on the moon. Okay? But we will always have some acceleration due to gravity, which we don't have in an x dimension problem. So that's the one main difference. So the problem says that a bowling ball is dropped on the moon from a height of 4 meters. Okay, so let's draw a little picture here. We have, say we're up on a cliff or something, and we have a bowling ball, and I'm not sure why we've taken a bowling ball to the moon, but we have. And the distance, the displacement, if you will, from where I'm going to drop the bowling ball down to the surface of the moon is 4 meters. So now remember that I always take my coordinate system, I define my coordinate system so that my initial position is always at the x equals 0 and y equals 0 positions. Okay, it's just easier that way so that when I do my equations, my x0 variable here, all right, my initial position, either in the x dimension or the y dimension, is going to be 0. It just makes it the equations that much easier to deal with. Okay, so I'm going to do the same thing here. So if my initial position is at x equals 0, or y equals 0, I'm sorry, then when it gets down here, what is this position down here? Well, if this is up and down as y, and this is 0, then down here, this is going to be y is equal to negative 4 meters, right? Because I'm going in the downward direction, okay? So my initial position is x equals 0, I'm sorry, y equals 0. My final position is y equals minus 4, okay? So x initial is 0, x final is minus 4 meters. And notice that when I use the variable x here, x just denotes position. X is a position variable. If you look at the subscripts, I is initial, y stands for the dimension. Okay, same as x, f, y. X is the position, f is the final position, and y is the dimension. Okay, so I know that. So I know we start at 0, we go to minus 4. The acceleration due to gravity on the moon is 1.6 meters per second, or 1.6 meters per second squared. Now, the acceleration is also pointing in the negative direction, so it's going to be negative 1.6 meters per second squared. Okay, so anytime we have the acceleration due to gravity, no matter if we're on the moon or the Earth or Mars or wherever, right, that value is always going to be a negative. In this case, it's negative 1.6 meters per second squared. Okay, so we know that. All right, so I drop a bowling ball from 4 meters. The acceleration due to gravity is 1.6 meters per second squared. Determine the time it takes for the bowling ball to hit the surface of the moon, neglecting any air resistance on the moon. Not that there's a whole lot of air on the moon, but there's a little bit. All right, we're going to neglect that. So what else do I know? Well, I don't know the final velocity because I want to know things just as that bowling ball hits the surface of the moon. So it's just a smidgen, maybe a smidgen away, okay? I can't say that the final velocity of the bowling ball is 0 because once the bowling ball hits the moon, then all bets are off. All kinds of strange things happen, right? And we're not accounting for those. I want to know all the information about that bowling ball just as it's a tiny, tiny, infinitesimally small distance from the surface of the moon. So I don't know V final. It's still moving when it gets just to the surface. Do I know V initial? Well, I'm holding the bowling ball like this, or holding it like this, I guess. One hand, I'm not going to be able to hold it with one hand. Two hands, I got my hands on the bowling ball, and when I initially let it go, for that infinitesimally small amount of time, before acceleration, right, can actually make the ball move, what's going to be the velocity of the ball? Well, the initial velocity of the ball will be 0, right? Anytime I drop something without throwing it down, I just drop something from any height, the initial velocity will always be 0 meters per second. Okay, so I can put that in there. All right, so I would like to know the time. That's what it's asking us to find. The time it takes for the blowing ball, it's a bowling ball, to hit the surface of the moon. Okay, so what equations can I use? Well, the second equation has V final in it, and I don't know V final, and I'm looking for time, so that's not going to help me a whole lot. The third equation has x position final. I know that. I know my initial position. I know my initial velocity, 0, all right, and I know my acceleration. Okay, so I could use the third equation, and as it turns out, that's really the only equation I could use in this case. So let's see what we got. We got x final, all right, equals x initial plus v0 times t, initial velocity times time, plus a half a t squared. All right, well, let's fill some things in here. So x final is -4 meters, and it is critical that we include the signs properly. Okay, that's why I made sure we understood that our position, our y final and y initial, we had the signs right. So x final in the y direction is -4 meters, equals x initial in the y direction, which is 0, plus v0 times t. Well, v0 in this case is 0 meters per second, so it's 0t, plus a half times at squared. Well, a is -1.6 meters per second squared times t squared. T is what we're looking for. All right, so -4 meters is equal to -0.8 meters per second squared times t squared. All right, I like to get t by itself, so I'm going to divide each side by -0.8 meters per second squared. And the answer I get when I do that is, turns out to be 5 seconds squared equals t squared. All right, if I take the square root of both sides now, I can get my answer, and it turns out to be 2.23 seconds. So the time it's going to take for that bowling ball to hit the surface of the moon is going to be 2.23 seconds. Hope that helps. We'll see you next time.